great pleasure to introduce Professor Baldi today from University of California. And today's talk will be on AI and biomedicine, the AI-driven hospital of the future. It's, as you probably some of you know, that's very related to what I do as well with my team here. So it will be so interesting to hear what you're going to tell us today. Thank you very much.
All right. Thank you very much for the invitation to speak to you and the hospitality. It's a pleasure to be here. And my group works mostly in AI and deep learning, in particular deep learning. We have projects in the on the theory of deep learning, and then a lot of applications in the natural sciences, in physics, in chemistry, and biology/medicine. Today I'm going to present the work in the area of biomedicine. I was told that that was the most relevant for this audience. So this is a picture of our campus. Actually, it's only half of the campus. My own office is on the left, not on the, you don't see it on the figure, but you see that we're not too far from a large body of water from the Pacific. So it is quite nice, and you're welcome to visit us anytime. And the joke is that UCI stands for under construction indefinitely. And I see that maybe it's something that resonates with you, because I see a lot of construction going on both in the campus and in the surrounding area. I've seen a lot of buildings being built. So we are under construction indefinitely, and if you were to visit us, this is the kind of construction you would see, which is a new hospital. We're building a new hospital on campus. We already have a large hospital complex 10 miles away from the campus, but now we're building a new hospital on campus, and that's very nice, but it's a little bit boring because it's a very, conventional hospital in many ways. And what I think we should really be doing is to build the new AI-driven hospital of the future. That would be the vision that I would propose if I were in charge. And since the administration doesn't listen to me, we decided to do it ourselves within the computer science department. I'll show you the department in a second. So what do I mean by AI-driven hospital of the future? I don't mean a hospital where there are no humans and only machines taking care of you. Of course not. It's a hospital where humans and AI work side by side and help each other. It's a hospital where AI progressively penetrates every possible process. So in a hospital, there are thousands and thousands of different processes, whether it's diagnostic, surgery, et cetera, et cetera. And so AI can penetrate in all these processes, and I'll show you an example of that today. All kinds of data, whether it's text, imaging, videos, time series, molecular structures, if you do drug discovery, for instance, et cetera. And at all possible scales, from the molecular level all the way to the population level, say, pandemics, etc. Doing so will help address some of the grand challenges of our time. We have problems with financial crisis, countries that have been printing too much money. Of course, global warming, and I'll show you how global warming, in fact, impacts certain diseases and risks of pandemics, etc. And there are geopolitical instabilities and so on. And in general, having AI in the hospital and driving the hospital and enterprise provides more precise, efficient, cost-effective, scalable healthcare solution for all. These are just, this is actually relatively old, it stops in 2004, but these are graphs that shows the sort of exponential increase of healthcare in the United States and other European and other countries. I don't know where Abu Dhabi stands on this plot, but I suspect it's much better than what you have in those countries. And of course, this exponential growth of the cost is a major problem and a reason for wanting to have AI in the hospital. And this is another graph just for the US that shows you, again, the non-scalability of things, because the number of MRI in the US alone has increased by 10% from 2016 to 2019, And the number of physicians that can look at those images has increased only by 2.7%. Right? So you have all these growth functions that are very alarming and are creating tensions and problems. In this case, for instance, either the physician will have to work extra hours, or the quality of the image analysis will not be as good, etc. And so again, these are good reasons for trying to find AI solutions to some of these problems. So this is the building in which I'm in, on the fourth floor actually, and that's where we're secretly building our AI-driven hospital of the future without telling our dean or our provost. It's very secret. All right, so AI is pretty much deep learning today. 90% of AI is deep learning, I would say. It's just a rebranding of neural networks, but with a few important twists and new drivers. In particular, computing powers, GPUs are very important for deep learning. Big data is useful, but I'll show you that you can get away also with smaller data sets. And of course, we have very robust and nice software libraries that everybody uses, such as PyTorch, TensorFlow, and so on. And to some extent, the neural network architectures technology has matured. And so, for instance, if you have images, you tend to use convolutional neural networks. If you have text, you tend to use transformers, and so on. Graph neural networks for structured data. So we have all kinds of technologies that are in place within the deep learning space. And so I'll show you an example of those different applications. So I'm going first to spend some time on a molecular level application, because I thought some of you are interested in the molecular level. So we're going to look at circadian rhythms. And then I'll show you multiple applications in the biomedical imaging space. So in biology, of course, there are all kinds of rhythms. The circadian rhythm is 24 hours. These are what you see in green are just the patterns. You're monitoring mice in cages, and you're looking whether they are moving or not. And you can see that you have this very precise rhythmicity, the 24-hour rhythmicity, alternation between periods of sleep and great activity. But there are also other rhythms that some are shorter than 24 hours. You have fast rhythms, for instance, in the brain, in the electrical activity in the brain, or longer rhythms, seasonal rhythms such as hibernation, etc. But today we're going to focus on the 24-hour rhythms, and these are very, very important. They were discovered for a few hundred years ago for the first time by botanists, because they took plants and they put the plants in the closet. And they saw that in the closet, the plant continues to move around as if it was following the sun, right? And in the dark, the plant does that for 2 or 3 days. And that's a sign that there is an internal clock. It's not driven just by the sun, by the external stimuli. There has to be something internally in the biology of the plant that causes this 24-hour motion. In the 60s, in the 70s, there was this Frenchman, Michel Siff, who used to go down into caves for a period of several weeks with all kinds of sensors attached to him. And so people started studying what happens to a human in the absence of light, etc. Does the 24 hours periodicity remains or changes, and all kinds of interesting things. But again, circadian rhythms seem to be a little bit of a curiosity. In fact, in your life, the only time you really think about circadian rhythms is when you travel and you have jet lag. And there you notice that there is something strange. But in fact, circadian rhythms are not something, some kind of a curiosity. It's a fundamental driver of biology. And if you really think about your life, you are a circadian robot. Right? Every day you wake up, you eat, you go to work, you come home, you eat, you go to sleep, and then repeat and repeat and repeat. Right? The reason you're not, upset that you have such a strong circadian master governing your life is that the circadian rhythms are very flexible. If you want to watch a movie one evening, go to bed 2 hours later, nothing happens. So there is a lot of flexibility, but on a large scale, they are extremely rigid. If you try not to sleep for a certain period of time, you die, right? So you cannot escape circadian rhythms. And of course, now we know that disruption of circadian rhythms leads to all kinds of disorders, sleep disorders, depression, obesity, metabolic disorders, aging, cancer, etc. Virtually any diseases has been in some way connected to circadian rhythms. And if you think about personalized medicine, precision medicine in the AI-driven hospital of the future, this is a table that contains all the top drugs on the left, the list of top drugs, and you look at their targets, and most of these targets, so now we're down to the molecular level, and I'll explain in more detail what happens at the molecular level. Most of the targets of these drugs are oscillating in a circadian manner. Their concentration in your body is oscillating in a circadian manner, at least in some organs. The organs are listed too. So you can imagine that if we had a deep knowledge of these oscillations, the amount of drug that you would give and the timing of the drug could be calculated more precisely. And that would, for instance, help avoid the side effects of drugs, because you could give smaller concentrations if you give them at the right time. Right? So we're very interested in circadian rhythm for these reasons. And we have developed two systems. One is called BioCycle. This is just a program that is going to take a time series of an omic time series. So it could be transcriptomic or metabolomic. You're measuring metabolites or gene transcripts in a given system in a circadian manner. So let's say every 2 hours, you're looking at the concentration of these molecular species. So you get a time series, and then you want to decide whether it's periodic or not, whether it has a period of 24 hours. And if it's periodic, what is the period, the period 24 hours, the phase, and the amplitude. And this is very noisy data. If you have ever worked with RNA-seq data or microarray data, very noisy data, very variable data, and you have replicates, etc., etc. And then we have circadiomics, which is a large repository of circadian omic data across all kinds of system, biological system, experiment, etc. And both are available to that, that URL in case you're interested in looking at them. So this is the BioCycle architecture. It's simply a deep feed-forward neural network, fully connected. You could imagine that in order to analyze periodicity of a time series, the best methods are Fourier analysis type of methods, but that's not the case due to the biological noise. We have tried those methods, but at the end of the day, we found that the best thing, what seems to work the best is a deep learning network, which has several components. One component is just a classification network that decides whether the time series is periodic or not, right? Whether this particular gene is oscillating in a circadian manner or not. And then if it is, there is a second network that estimates the amplitude, the phase, so these are regression value. And then we also produce statistical measures such as p-values and q-values. What is interesting about this application is that it can be trained entirely with synthetic data, which is a little bit surprising that something practical is trained with synthetic data, which is of the kind that I'm showing here. But basically the idea is we can generate signal with mathematical functions, sine, cosine, putting a linear trend, an exponential, etc. So we can generate a lot of different signals. We can tweak their noise levels, the level of replication. You know, if you're doing this in mice, how many mice you're measuring your signal on, etc. And that's what we use for training the system. And if you think about it, what are the problem where you can use synthetic data and be successful? Basically, it's going to be every time you're trying to train a neural network to predict some mathematical property like periodicity. Think a network that looks at a graph and computes, say, the chromatic number of the graph or something like that. That's another application where you could train it with synthetic data derived from mathematics, right? These are the ROC curves comparing biocycle to other systems. I'm not going to go into details, but it shows that it works very well. And what you can do with that, when you combine it with circadiomics, for instance, you can look at, so circadiomics is this large repositories with hundreds of circadian experiments. We can look at which genes are circadian in these different experiments. And then we can build a histogram that tells us which gene is found to be circadian most often across all those experiments. These particular examples are done in mice, right? And so we build this histogram. And then if you look at the most frequent oscillating transcript, the blue ones on the left of the histogram, you rediscover something that biologists have discovered in the last 20 years, which is the core clock. So the core clock is this circuit here that is present in every one of your cells, which is sort of the center of circadian rhythms at the molecular level inside any one of your cells. You have two transcription factors called clock and BMAL that can dimerize. They bind to the promoters of many other genes. They're very promiscuous. They bind to something called E-boxes, which are very degenerate motifs in the promoters of many genes. And they, by doing that, they activate the expression of those genes, so genes like CRY, PER, etc., which then, of course, are translated. And in time, they form a complex that comes back in the nucleus and inhibits the production of clock and BMAL. So you have a classical transcription, translation, feedback, inhibitory feedback loop that has a periodicity of 24 hours. And so this is really the center of your circadian rhythms at the molecular level present in every one of your cells. So that is nice. But when you do a circadian experiment, what you find, so this is called the core clock, as on the order of, let's say, 15 genes in total, right? But when you do an experiment, a circadian omic experiment, what you find typically is that the number of genes that oscillates is much larger than 15. It's more like 2,000, right? It's about 10% of genes of transcripts are oscillating in any one of your cells, in any one of your organs or tissues, right? And this is under different conditions. And so you can see here, for instance, 3 experiments where we do a genetic change, a mutation in mice, or a diet change. You change the diet, you have mice raised on a high-fat diet versus normal chow, or you can look at different strains of mice, etc. Whatever you do, you see that the number of oscillating transcript can be on the order of 1,000 to 2,000, so 10%. But you see also that they are different. The intersections are different, right? So if you look at, let's say, your liver cells and your brain cells, they all have about 10% of their genes oscillating, but the 10% is different. The intersections are completely different. Usually you find the core clock is common. Those 15 genes, you find them almost everywhere. But there is a lot of stuff on the fringe that is oscillating that is not part of the core clock. So that's an important discovery of the last 2 decades or so. So these are many experiments that we did, and you can see a matrix that tells you, what's the size of the intersection, etc. And you see it's all over the place. This is for transcriptomic. We have done the same thing with metabolomic experiment. You see the same thing. So roughly 10% of your metabolite are oscillating, but the 10% is different depending on the condition, depending on the diet, depending on the tissue that you're looking at, etc., etc. So these are the main finding. The core clock contains only 12 of genes, but in any tissue or condition, there is 10% of genes, transcript metabolites that are oscillating. The overlap across tissues and condition is relatively small. Any genetic or environmental perturbation results in massive changes in terms of what is oscillating. And so the question is, how is this even possible? Right? It's very strange, if you think about it, that throughout your body, you have a lot of oscillations. Every cell roughly has 10% of its transcript that are oscillating, but the 10% are very different depending on where you are in the body and what is going on in your environment, what kind of food you're eating, etc., etc. So to try to explain this, we're starting to build a theory, but you have to think about the circuitry of a cell. You have seen picture like this. It's always very complicated. And if you think about what is it that can oscillate in a cell, it's not a single transcript by itself cannot oscillate, or a single metabolite cannot oscillate. The only thing that can oscillate is when you have a loop, right? A species A regulates B, regulates C, etc., and then it comes back. So only a loop can oscillate, not an individual molecular species. That's fine. You have all kinds of loops in a circuit like this. The question is, why would the loop oscillate with a 24-hour periodicity, right? And the answer to the question, this question is, of course, evolution. Because if you think about evolution, if you think about evolution, life started, 3.5 billion years ago or so, and some of the first organisms were cyanobacteria, which are a photosynthetic organism. So if you are photosynthetic, you are circadian almost by definition, because all your energy, your metabolism is linked to light, right? So the very first circuits of life had this 24 rhythmicity embedded in them because they were photosynthetic. And if you think about evolution, how many times the Earth has rotated on its axis since the beginning of life, 3.5 billion years ago? You do a calculation, you find about 1.3 trillion times. It's actually a little bit more, it's 2 trillion times, because the speed of the Earth around this axis has changed over time. But basically, 2 trillion times the Earth has rotated on its axis, right? So this is a rhythm that is absolutely relentless, and it's the most predictable thing in the environment. The world during the day and during the night looks very differently. You have different predators, different temperature, winds, tides. Things are very different, but this alternation is very predictable. It's in fact the most predictable thing in your life is the fact that there will be a sunset tonight, there will be night, and then day again tomorrow, right? The rest is very unpredictable. And so evolution, of course, had to pay attention to this regularity and build it into the circuitry of life. So basically, in any one of your cells, you have those very complex circuits, a lot of loops, and what I'm arguing is that because of evolution, the fundamental frequency at which those loops can oscillate is 24 hours. Right? And so the question now becomes, in a given situation, you have a bunch of loops, maybe 100,000 loops that are oscillating. In another situation, you have another set of loops that is oscillating. How does the cell know or organizes these changes in oscillation? And this goes back to the core clock, where you have many transcription factors in the core clock that can bind to many other promoters. And so that's what we call the architecture of circadian rhythms, and that's what we're studying now. It's really the hierarchy of promoters that are controlling these oscillations in transcription. But I don't have much time, so I won't go into that. And I'm going to shift now to the application in biomedical imaging for the AI-driven hospital of the future. So in imaging, we typically use convolutional neural networks. They were introduced by Fukushima in the 70s. He introduced this architecture, which he called the neocognitron, but it's basically convolutional neural network, very much inspired by the work of Hubel and Wiesel in the 60s, who discovered that in the brain, you have arrays of cells that are doing sort of a feature detector operation, detecting, for instance, vertical bars at every position in the visual field, or bars at 45 degrees, et cetera, et cetera. So you have this idea of convolutional operators that are applied to the visual field. And that's what Fukushima used to build this architecture. The only problem he had was the learning algorithm. Fukushima said, we're going to train the weights of this architecture by Hebbian learning. That's the only algorithm that he knew at the time. Hebbett presented this idea in around 1950. And in 2015, we showed that actually you can never train such an architecture by Hebbian learning, will never work. What you need is something else, which is, of course, gradient descent or backpropagation when you implement it using the chain rule. And so in the 80s, when we started using these networks, using gradient descent, that's when we saw that they could do well on image processing. And I think this is the first application of convolutional neural network to biomedical images, as far as I know. In this case, it's a biometric application where we had what you would call today a Siamese convolutional neural network, where you could, in the input, you could present two images of a fingerprint, and then this is in this case, it's a classification network. In the output, it would tell you whether two images come from the same finger or not. But we knew that these methods, this convolutional neural network, work very well. And today, of course, the applications are exploding because we have GPUs, because we have TensorFlow and PyTorch, etc., etc. So let me show you some of our applications in support of the AI-driven hospital of the future. This is work with Chris Hughes, a biologist at UCI, who has a technology where he can grow blood vessels. What you see in green are blood vessels in little wells. So you have 96 well plates, for instance. You're looking at them with a microscope, and in this well you can grow blood vessels, you can grow cancer cells, you can grow mini organs, etc., etc. And in this slide, I show you cancer cells in blue. And of course, what you want, you can give a drug, for instance, to one of these systems. And of course, what you're interested in is to see whether the vasculature has changed, whether the number of cancer cells has increased or decreased, etc., etc. And this is a high throughput technology. It can produce hundreds, if not thousands of images per hour. And you don't want to have humans looking at these images deciding, yes, the cancer has shrunk or not, right? So again, we train convolutional neural network on this task, and you can see the ROC curves. They can do this task very well. So this would be an application for basic research on cancer. This is another example. This is using brain imaging, detecting genetic mutations. Again, in collaborations with doctors at UCI, we developed a convolutional neural network for doing that. That worked very well without going into details. This is another example detecting cancer metastasis. When you have cancer and it tends to metastasize, the first target, most frequent target, are the lungs, then the liver, and the third one is the spine. So in this case, we're detecting whether there are cancer metastases in the spine, and if there is one, in which vertebra it is located. Let me spend a little bit more time on this application, which is the detection of polyps in colonoscopy. So in colonoscopy, you're basically looking at the colon, you're trying to find polyps, and the doctors typically want to remove these polyps because this is where colon cancer begins. So in collaboration with Dr. Kearns at UCI, we were able to assemble about 7,000 images of the colon with and without cancer. And then we trained a convolutional neural network to do classification. You can even train them to put bounding boxes around polyps when polyps are present. You can see the ROC curves, it's quite good. It's pretty much at the level of human doctors. And what you want is to build a system that can help doctor identify polyps, because the area of the surface of the colon is about the surface of a tennis court, and a colonoscopy takes 5 minutes. So it's not uncommon for doctor to miss polyps, right? So you would like to build a system that can help doctor find polyps during colonoscopy. And what I showed you is a system that is trained on images, on frames. So the question is, can you apply it to video? Because that's what you really want to do in colonoscopy. And the question is yes, and it's actually very easy, because when you train a classifier like this, training may take weeks, depending on your data, on GPUs, on the size of your network, etc., on those details. But once trained, a CNN can produce an output very quickly, something on the order of 20 milliseconds. So if you have a video, You don't have to do prediction at every frame. You have 60 frames per second. You just predict every 10 frames is enough, for instance. So what I'm going to show you now is our system in action. You're going to see video clips of the colon during a colonoscopy, and you're going to see our system, our AI, putting bounding boxes around the polyps in real time. It's the same as accuracy, as I said, as a good doctor. Sorry to show you this before lunch, but I told my student to put some music in the background. They told me I was crazy. Now, down the road, you could imagine having a little pill, a little robotic pill that has a little camera, a little scissors, and you just swallow the pill and it goes through your system and it takes care of all the polyps. And you can do similar things for problems in the stomach, for ulcers. You could imagine any kind of endoscopy. This pretty much shows that you know, the technology for doing it is there. Now, if you were to build such a pill with the technology that I just presented you, you would have a problem because you would see a bounding box, would cut around the bounding box, and you would bleed to death. What you really need is an AI computer vision system that can find the contour of the polyps. And that seems a much harder problem because the contour is a subtle thing, but you can see we solved it with a little bit fancier architecture and a few tricks. But you can see now, again, video clips of colonoscopy and our AI system putting the contour, delineating the contour of the polyps in real time. And this is actually being used now in the hospital with real patients. Again, it's not meant to replace the doctor. It's just something that works together for the doctor. You can make it, you know, you can change the interface, make it beep every time there is a polyp, etc. But it's a tool that helps to speed up and make colonoscopies more precise. And by the way, a few weeks ago, there was an article, I don't know if you saw it, that claimed there was a large study done in Scandinavia that maybe colonoscopies are not so useful for preventing colon cancer, right? From an AI standpoint, this is not a big deal. We just remove one program from our suite of programs. So it's very easy to handle these changes if you are doing everything at the AI level. Right. Let me show you another example. This is eye surgery, right? Doctors are very interested in tracking something called the trabecular meshwork. It's the TM that you see there. It's a very fine line that is actually quite difficult to see and to track, but it's an important anatomical landmark. And so this is, again, our system that is tracking the TM in real time. This is just the beginning of a much larger project where we're trying to develop tools, AI tools for eye surgery. But the most, let me skip this. The interesting thing is this. When you're doing eye surgery, right, you have to shine light on the eye. And sometimes for a couple of hours, 2-3 hours. And this is very toxic for the eye. You're going to burn your photoreceptors. When you come out of those surgery, you are blind for several days if you're lucky, and permanently if you're not so lucky, right? Because you have to shine this light, strong light with a lot of energy on the retina, on the photoreceptors. So we want to build a system where you can shine light of low energy, infrared light, right, on the eye, on the retina. And that's good for the eye because you have less energy, it's less toxic. But the problem is that the surgeon is not going to see things well if you illuminate using near infrared radiation, right? And so we're building a deep learning layer, an AI layer, that takes the infrared, the image obtained with the low power light, low energy light, and converts it. It's called the colorization problem, puts the color back as if it was obtained with the regular light. So if we succeed in doing this, that will be an important breakthrough for eye surgeries. This is an example not from me, but from one of my colleagues, where we're looking at the ultrasound of the heart, essentially, and inferring all the blood flow in all possible directions. Again, using essentially deep learning technology. Another thing I want to point out to you that for which AI is very important is the sort of economy of scales that you can do. And let me explain that to you. In this case, we're looking at mammograms. So these are X-ray of the breast. There are millions of mammograms done in the US alone and many more, hundreds of millions around the world each year. And these are made primarily to detect cancer in the breast, right? So you can train a convolutional neural network to classify mammogram images into cancer, non-cancer. You can localize nodules. You can do all that, that's fine. But it's in this particular experiment, we do something completely different, which is to measure the level of calcification in the breast. So we're looking at the blood vessel and we're trying to infer the degree of calcification. And you can see in the lower right, the curve where you have the true level of classification assessed by human radiologists, by human expert, versus the predicted level of calcification predicted by our AI system. And you can see there is very good linear correlation, right? And so it's almost perfect. So we can measure the level of calcification in the breast from the mammograms. And the reason to do that is that if you have a high level of calcification, potentially it's a sign of heart disease. So as a byproduct of you having a test for one disease, breast cancer, we're looking for other diseases using different parallel systems in AI. So you could imagine every time you have a test of any kind, imaging or other, you have 20 different AI programs running on that data, looking at all kinds of other things that doctors are not doing today. And so you have economies of scales that can be done using this approach. Another example, this is not a convolutional neural network, but it's just a standard neural network, is a follow-up of patients through surgery, right? So you have, of course, you have recordings, if you can get your hands on, you have recordings of all kinds of physiological signs, blood pressure, heart rate, etc., throughout surgery, before surgery, during surgery, after, together with clinical data. And you can use that to predict some post-operative outcomes. For instance, what is the probability of you dying, or what is the probability of you having kidney failure after surgery, etc., right? And so we can use all that data and deep learning to make those predictions in very efficient ways. Next, I want to show you examples in other areas. The same technique can be applied in other areas, for instance, in veterinary medicine. Right? There is no reason to use them only on humans. You can use them also on animals. So this example is done on dogs for a disease called valley fever, which is becoming a big problem in the southwest part of the United States because it's caused by a fungus. And if in areas that are dry, it's found in the dust, so dogs who are sniffing the ground all the time can inhale this fungus, it gets in their lungs, and it's very toxic for them. And so it's becoming a problem, and because of global warming, we expect the disease to expand. The current prediction is that it will go all the way to Canada. I'm not sure if it is present here, I haven't looked, but that would be an interesting to look at. The Army, for instance, has a dog training facility in Arizona. And so they are very worried about this sort of things. So again, you can do X-rays of the lungs in dogs, train convolutional neural network to detect whether or not valley fever is present. You get very good ROC curves. These are just different, comparing different architectures, different types of networks. Those are details that you can look in our papers. And on the left, you have an X-ray of the lungs of the doctor. On the right, you have the heat map that you can do to improve the interpretability of the system, to understand what are the regions of the input that have caused the system to classify this particular X-ray image as a case of valley fever. And by the way, keep in mind that the anatomy of dogs is much more variable than the anatomy of humans. So you need to have training sets with different species of dogs in the training set, etc. So there are also interesting questions from that point of view. But this shows that, of course, we can apply the same techniques to dogs. Maybe in this area, camels could be interesting. Maybe there are specific diseases that camels have that people want to detect, and one could perhaps look into that. Okay, so this is a diagram that shows you the boundary between what we can do today with AI and the things that we cannot do yet or that people are working on. And an obvious one is sort of reasoning, fancy form of reasoning. I would argue that for the basic hospital of the future that I'm trying to describe to you, you don't need very fancy reasoning. In fact, a lot of things can be done by simply very simple rule-based system. For instance, my current healthcare provider has me do a lipid panel, a blood test, maybe once every 2 years. And then I get an email that says, your cholesterol level is quite good, but your good cholesterol is a little bit low. You should try to exercise more and eat more omega-3s. And omega-3s are found in salmon and avocado, right? That's a completely rule-based system. It's something we can do now very easily. You don't need very fancy reasoning in this basic version of the hospital of the future. Nevertheless, we are very interested in reasoning, and so we study more advanced form of reasoning. So I'm just showing you one example here, the Rubik's Cube. We have developed a system that can learn automatically how to solve the Rubik's Cube, basically using deep reinforcement learning. So you see here a scrambling of the cube, and now the AI solving the cube. So you see the solution. For instance, R means turn the right face clockwise 90 degrees. R prime, turn the right face anti-clockwise 90 degrees. And this is, of course, the Rubik's Cube is all about mathematics. It's a group theory, basically. So you can see that that's one approach to reasoning in this very confined system. All right, so my conclusions are that AI-driven hospital of the future is actually already feasible today. The technology is already available. We could put deep learning, CNN, and all kinds of other AI methods inside all kinds of processes in current hospitals. We have the tools such as transformers for text, graph CNN, graph networks for, let's say, drug discovery, etc. The CNN in particular are very effective for all the imaging problems across all kinds of modalities and sensors. So it can be images, it can be videos, it can be microscopy, pathology, X-ray, MRI, PET, etc., ultrasound, endoscopy. All of these basically can be handled with high accuracy using the CNN or variation of those. People are now starting to use transformers on images too. The key is to get training set. It's the data, that's the key. So you have to collaborate with doctors, with people in the application area in order to get data and labels. It used to be that you needed very large data sets, but more and more we can deal with smaller data sets using a number of techniques. I've listed 3 here. Data augmentation, if you know the right way of perturbing your data, maybe rotating your images, adding Gaussian noise or whatever, it depends on the application, of course, you can increase the size of your training set effectively. There are techniques for regularizing the networks, dropout, etc., etc. And then very importantly in this area, it's the reuse of pre-trained networks. So you have networks on the web, such as BGG16, ResNet, etc. You probably know those that were trained, let's say by Google or Microsoft on very large databases of images to recognize everyday objects, trees, car, pedestrians, whatever. And so you can take those networks already trained, you have all the weights, you just remove the top, you replace the top with a few fresh neurons, and you retrain this architecture, right? So you have very few free parameters. Most of them were trained on a different application, but they're still useful because, you know, an edge detector is an edge detector. You don't need to retrain edge detectors every time, right? And that's pretty much what a doctor does, right? The visual system of the doctor is not trained on X-ray images, right? It's trained as a child on recognizing, you know, people and toys and things like that. Only during medical school is, you know, a couple of months you get trained on those specific images, cancer images or whatever. So we are basically recapitulating that in this sort of approaches. You can apply these techniques, of course, beyond the hospital setting to, I gave an example in veterinary medicine, telemedicine, of course, providing, you know, point of care for people who work, let's say, in rural areas or remote areas where there are no hospital or very few doctors. A typical example would be skin cancer, right? You can use your cell phone, take a picture of a mole, send it to the cloud, and there you could have an AI that looks at the picture and you know, provides you some advice of whether this lesion that you have, this mole that you have, is potentially cancerous, and you should really go and try to find a doctor, or whether you don't have to worry about it very much. Interpretability, people working on deep learning or deep learning application are always worried about the black box problem, the fact that neural networks are opaque, etc., etc. I don't think personally that it's a major obstacle for a number of reasons. There is work on developing more explainable architectures, of course. There is techniques for producing heat maps. I showed you example with the dogs where you can see which part of the image is responsible for the particular response that the network is giving to you. Encapsulation is very important. So decomposing a problem in many sub-problems, right? And having this decomposition always present to you is very useful. I'll give you an example. When we built the colonoscopy system, right, we were getting a lot of false positives and we didn't know why. Okay, so then this was at the classification level. So then we put the localization layer, that is where we put the bounding box. So now when you have the bounding box, you know at least what is the part of the image that causes the false positive. So we started looking, all those false positives, there was a box, in the box there was a surgical instrument. So what was happening is that the system had noted that usually there is a surgical instrument near a polyp. So as soon as it saw a surgical instrument in the image, it says, yes, there's a polyp, okay? Which of course is wrong, but now you can detect what is going on because you have decomposed the problem in yes or no, where, etc. Then we have the contour. So if you can decompose the problem in different sub-problems, that helps you find errors, false positives, false negatives, etc., etc. Reasoning, general artificial intelligence are great challenges for us to do research on, but they are not major obstacles for the applications that I described to you. I believe you could build an AI-driven hospital without very, very fancy reasoning, at least not at the beginning. Most of the processes that I see can be taken care using the methods I described. The major obstacle really are human obstacles, social, political, organizational, legal, which require other approaches, which require, you know, teams of people working together, both on the medical side and the AI side. And these problems are different. Each country is different. Each country has a different healthcare system. So there is not a solution that works everywhere. Every geography is going to need to have specific approaches tailored to the particular environment. And so those are actually the most difficult problems. It's not the technology is in place. All right, thank you very much. I'll be happy to answer any questions.
Thank you, Professor Baldi, for the insightful presentation. We will take a few questions from the attendees here, please. Yes, please.
So I could start with one about polyps detection. Can you tell us a little bit more about
Was that deployed for clinical practice or was it just for research purposes? So is it applied to patient?
Yes, it is applied to patients.
So that leads me to the question of the regulation. So because I've been through this before, and when it comes to regulating that or FDA approval, it's a nightmare. So tell us a little bit about your experience in that.
I concur with you. It's a nightmare. That's fine. But it's a nightmare. And, you know, as somebody who is interested in AI, I actually, to tell you the truth, stay away from that because I don't have time. I just move to the next interesting AI problem. I work on the AI. But in this case, yes, the doctors started the company. There's actually a company that was created called DogBot. And, you know, because, you know, a single doctor can start using the system during colonoscopy, doesn't need a particular permission because he's still doing the colonoscopy. He's just getting, you know, additional information on the screen from this type of AI system. And so that's the way it started working its system through real patients. But then at some point you have to do clinical trials, etc. Right? So it's a whole process. And if you want to do it as a business, there is a big issue, which is what is your business strategy? You know, you could work with the people that manufacture the scopes that are used during colonoscopy. There is 2 or 3, you know, Siemens, and there's Olympus, a Japanese company, whatever. So probably in the end, I would imagine that those companies will integrate the AI with their system, right? They sell you the scope, the screen, and the AI all together. But who knows? Maybe there is a way to do it separately, or that's a business strategy. So you have to create a startup and look at different, you know, drive strategies.
A similar system to that is actually deployed in some hospitals here in Abu Dhabi. And it took, I know that story, but it took a long time for it to be used on patients.
Oh, so
yeah, so the question is about, like, you have the hospital of the future, AI-driven hospital of the future. So coming back to regulation, do you think that we're far away from having more smooth way of deploying things to patients? And that will be a bottleneck when because we have so much research on developing AI solutions to different medical problems.
I definitely think the bottleneck is human. In the US, it is huge. I cannot speak for the healthcare here, but in the US, it's huge because, you know, you have the doctors are afraid to lose their job. The lawyers are afraid of lawsuits, patients saying, oh, you didn't find my polyp, it's because you were using AI, you know. So every stakeholder is a problem, right? So you really need to create a movement where people come together, they see the benefit of the AI. So, you know, you have to change the culture. It's a very big problem. It's not going to be solved in a few months, etc. It's for the next few decades. But the amazing thing is that the technology is here today. And I think the majority of people, lay people, don't know this. So education of the population is also very important. It's an important element in solving this. But, you know, again, legal issues, employment issue, because in principle, I think in the long term, you could replace radiologists with this technology. So you're going to have to recycle all the radiologists and, you know, change the curriculum. It's a long-term, you know, long-term project, but the solution also for us, I think, is to start with specific problem, whether it's colonoscopy or eye surgery, etc. And, you know, you drive that particular sector. You cannot fight all the battles at the same time.
Okay, other questions, please? Yeah, the rate of adoption, I mean, from your experience in the States, in your part of the world, in Irvine or around, how is it? I mean, it has been now almost 8 years or 6 years since.
Okay, it's not very good. It's not good. Let me tell you something. Okay. I am in the system of University of California, yes, right?
Yes, yes.
We have, you know, I don't even know, you know, on the order of 10 campuses. Yes. On the order of maybe 7 or 8 big medical schools, UCLA, yes, UCSD, UC San Francisco. Yes, yes. If you could join those hospitals, I think it's like 15 million people on which you would have all the records, all the images, etc., right? But transferring data from, let's say, UCLA to UCI is a nightmare. Wow. It's a complete nightmare.
Can I add one thing to that? So 2 months ago, I was at a major conference in Singapore. So keynote speaker was a well-known professor, Ding Chen, in China. So he, in his talk,
they were saying that when they develop a deep learning solution for specific problems such as lung cancer, he simply says, we deploy it to 600 hospitals. So what I see now is that in China, there's an amazing work done on deploying deep learning solutions to medical problems that all of the world is not doing that. And I think people will lag behind on this.
It can change dramatically from country to country. And maybe you have an opportunity here.
Yeah, that's true. That's true.
It's maybe easier to do it.
And UCI has been a leader actually in sharing data sets.
Yes, yes.
I mean, in various things, including the medical. So
Absolutely.
yeah, we need to give
Yeah,
credit
the
to this
poly data
university.
set will
Okay, if no more questions, we thank Professor Baldi for very insightful talk. Thank you so much.